Okay, welcome to the video presentation. I'm Arne Pohjonen. I'm currently working as postdoctoral researcher at University of Oulu, and here is my current contact information. I am describing application of two-grid interpolation to enhance average gradient method for solving partial differential equation. In our previous study, I used the method for calculating average gradient at the grid points, which operated by fitting a plane equation to different regions. So here, as an example, if we want to calculate an average gradient at this point, I will fit the plane equation to the neighboring grid points for each of these regions. So for the region R1, I will use these 3 points, and for R2, these 3 points, for R3, these 3 points, and R4, I will use these 3 points. And then I will calculate the local average gradient based on the weighted average of these each regions. And this method allowed me to calculate the gradients in deformed grids, which is a kind of a step forward from the usual finite difference equations. But there were some issues, mostly for the sparse grids. There is inaccuracy and this kind of instability, which is it's seen as the oscillations in the numerical solution. Okay, this could be solved by increasing the number of grid points, so making the grid more dense. But if we had this kind of initial conditions such that there are large discontinuities, the method was unstable, and it worked well for the smooth initial condition. But in the case of if the solution is such that at some point there occurs discontinuities, or there's large changes in the field, this kind of instabilities start occurring. And for this reason, I started to look at kind of better way of doing it, and that uses interpolation. And even in this earlier study, I used some interpolation near to the maximas and minimas of the field in order to enhance the solution. But this current study kind of takes this idea to further, and I use interpolating grid. What this means that first we have this triangular grid, and then I use interpolation points between each line of the triangle, and the interpolated grid and the original grid points are shown in this figure. So the original grid is the black circles, and the interpolating grid is the red crosses, or that's the denser grid, which includes both the original sparse grid and the interpolating grid points. I also tested this method using ordered grid as well as deformed triangular grids. This is important because I want to use this method in the cases where the material is being deformed, and then I want to solve the partial differential equations. And so I have to make sure that this method produces correct results even in deformed grids. Okay, here is validation of the mathematical model. I calculate the solution for diffusion from it's a diffusion from a initial point, initial concentration point and they compared the result to an analytical solution. The solution is in 2D, and I'm plotting it along the x-axis, along the line which crosses the origin. And I'm comparing the results to the analytical solution in a similar way that I did earlier, but now I'm using this triangular two-grid method. And then I did the same thing in the case that I have deformed grid, and made sure that the simulation corresponds to the analytical solution. So I made this validation, check that this is the case, and that kind of shows that the approach is valid and it can be used in the studies. Thank you for listening to the presentation, and if you have any questions or corrections or want to collaborate, please, you can contact me. Of course, it's always limited in time, what kind of collaboration is possible, but it's nice to hear if you have some ideas and we can discuss. Thank you.